short recap of the previous episodes. Cojac for Java is a free tool able to boost at runtime the power of Java numbers so that they get new skills. When running any program in Cojac mode, your plain old numbers can shout when they see suspicious things happening in your computations, use interval computation to quantify the numerical error margin, compute with many more significant digits, and even bring derivatives as a byproduct of the computation itself. That last feature, automatic differentiation, is available in two different flavors. In the forward mode, you first tag one of your data, say an input x, as being the independent variable of interest. Then you automatically gain access to the derivative in x of any computed result. Symmetrically, in the reverse mode, the focus is put on one of the results that you announce as being the dependent variable. Once that output data is marked, you automatically have access to its partial derivatives in any available data. Cojac integrates both modes in a quite spectacular way, as the computation code is left totally untouched. Some autodiff tools are more efficient, but none brings a front end more elegant than Cojac. Just to clarify, if the topic is new for you, automatic differentiation is completely different from a numerical approximation where the function is evaluated on successive points to estimate the slope. And it has nothing to do with a symbolic approach where the formulas themselves would be stored as a data structure. If you want symbolic processing, choose an environment like Mathematica, where the computation model is radically different. Symbolic features cannot magically appear inside Java floats. Don't dream. Stop! Why not dream? In the Cojac team, we love dreaming. And indeed, although your formulas are not supposed to survive in memory, they do not completely disappear, but they are hidden in the bytecode. And yes, Cojac is able to rebuild at runtime those expression trees that the compiler buried as a sequence of commands. In this expression, for instance, there is normally a small rounding error. Remember that writing 0.1 is always misleading, as 1/10 has no finite representation in base 2. But when you run that in our symbolic mode, the evaluation applies on the whole computation tree. And Cojac recognizes a pattern where the same sub-expression appears in the numerator and the denominator. This triggers a simplification rule. When you inspect the internal representation, you can see the rich structure behind. This example only scratches the surface of our symbolic numbers. Here is a method that takes an array of numbers and computes the sum. That code is shocking only for those lucky ones who remember the nice recipes from their numerical analysis course. An improvement would be to reorder the elements so that the smaller terms are considered first. An alternative is to apply the compensated sum algorithm to reduce the overall rounding error. With Cojac, you get those algorithmic refinements just with a runtime flag. If you've seen something similar in another programming environment, please let me know. With symbolic expressions, you reach a very high level of enrichment for a number type. But there is still room for a step further, where the word symbol will really come into play. We can tag a number so that it becomes the unknown x, and then we call an existing Java function. It has a return value declared as a floating point number, but the data you get at runtime really holds a symbolic function of x. Cojac gives you a means to display the internal formula, to evaluate it at an x value, or to build the derivative. But we could also expand the prototype to solve equations in a symbolic way, integrate, find the extrema, and so on. The methods you wrote in Java do not at all need to be adapted. You just receive new toys to leverage that code in unexpected ways. When you start exploring that new world where a single number represents in fact a whole function, you might wonder if there are other ways to represent it internally. One smart alternative is to approximate the function with Chebyshev polynomials. They have very nice properties so that you can handle symbolic requests and behind the scene rely on numerical methods like the FFT. In a certain way, it forms a miraculous bridge between the two models. This idea is the basis of the ChepFun package, a marvelous library for MATLAB. Yet, in my opinion, there is one annoying flaw with ChepFun. You still have to modify several details in the source code of your functions. We have implemented a mode in Cojac that partially simulates ChepFun in Java. I think it's more than just a port of ChepFun. It's the first time the IDE is integrated in a programming language so that the source code of your application kernel is left totally unchanged and you decide later whether you want to run it under three totally different computation models: numerically, symbolically, or via ChepFun, which combines ideas from both worlds. Okay, I agree. With such a feature, we are a bit far from the day-to-day activity of a Java developer. So let's lose altitude and fly closer to some more common needs. Consider a practical case where you would like a rough idea of the numerical stability of a program. A popular trick is to settle a different rounding mode and restart the job, just to see what happens to the final results, with the hope that the impact is not significant. Java itself doesn't give you control over that CPU setting, but with Cojac you have that power to switch on the roundup mode for a run or the round down for another try. Another way to slightly change something in the behavior is to compute everything in simple instead of double precision, replacing all doubles with floats. Cojac is able to do the job for you automatically at runtime. It can give you even more. Applying the nice principle of delta debugging, it can discover itself a maximal subset of the computations that may safely be done in simple precision considering the requested accuracy. To sum up, you have on one side plenty of Java code based on standard numbers, all those modules already existing or still to be written to analyze and transform your data. Computing is at the core of your applications. On the other side, you have plenty of richer number models which have wonderful features but are still mainly underused. What was missing is the exceptionally gifted animal able to establish new connections between all them. Our prototype for such a beast is called Cojac. Maybe someday it will be common for a developer to juggle with different computation models, and the programming environments will embed them natively. Or perhaps the machine will learn to switch from one number system to another, depending on the context. Who knows? Our project is exploring what is possible in the current technology. For no specific reason, only scientific curiosity and the pleasure to try different things. We do have other ideas for new features to add to Cojac. Stay tuned. For now, all we need is love, yes, of course, but presently some feedback would be welcome. We propose an unusual tool. It's free and open source. Don't you agree it's a wonderful toy to experiment and discover some great ideas? Could it even be useful? Your opinion would be highly appreciated. So don't hesitate to share your comments. Thanks in advance.